you see the first lesson of the class, also the first lesson of this week. We see the earth moving materials and operations for construction method and management. And every week we cover roughly 2 lessons. And this is the first lesson of this week. We have 4 learning objectives. The first one is recognize the importance of construction method and management, which is the subset of this class, to the engineering education. Underlie the cost policy and procedures. These 2 learning objectives I will cover during the synchronous sessions. And for the video lessons that we cover for this video and the next ones, we will discuss for the last 2 learning objectives, with either relate the general and construction characteristics of soils to earth moving operations. That is one of the construction method we learn for this class. And we estimate the earth moving volume to understand the operation of the earth moving and determine the volume, so that we can determine production and also the costs that cover in project planning. For example, we need to know the and review the soil volume change characteristics, how the volume of the soil change from this condition to the other. So this portion I will repeat in lesson 2 of project plannings, because that some of you will not take take both classes, so I have covered that as well. Other than that, it will be 2 different class in there. The purpose for that to do the cost estimate. This one, the operation, the method, construction engineering side of the project. So for this one, let's talk about how the volume change. And let me go to slide that we have. So every lesson I have a short slides PowerPoint that captures some figures, graphic, equation, etc. for the class. So what does that mean, the soil volume change characteristics? As you can see, when we do the earth moving problem, the earth at the natural condition that we call bank condition, and then you use the excavator, salvo, etc. to excavate, disturb the soil, and put it on the dump truck, and that become a loose condition. And when to transport that to a final site to compact it, and that it become a compacted condition. And the volume will be changing from this condition to the other. To show that change, and I can show you here for this, it will be from the bank condition. As you can see, the soil, in terms of soil, they have 3 states. As you can see, soil, water, and air, and then soil, water, and air. But because of the disturbance from the natural to the loose, the air volume increase, associate the volume of the soil increase. So basically, the change from the bank condition on the left to the mid or the loose condition, the volume is increasing because the air volume increase, and that we change that we call swell. Okay, and then when we put that loose condition in the site, compacted, the air reduce, the soil remain unchanged, right? The solid soil, the air reduce, the volume of the air reduce, so that the volume at the end of the compacted condition is less than the volume at the bank condition, and that change we call shrinkage. And as you can see in this graphic, so shrinkage is changing between the bank and the compacted, not between the loose and compacted. Keep that in mind in that one. So as you can see, if you study geotech, of course, geotech 1 you study this graphic tend to be familiar to you, the horizontal water percent and the dry density of the soil. And as you can see, at the bank condition, the soil is at that much, and then the density will be reducing when it too loose, because the volume reduce. And as you can see, density equal to the weight divided by the volume. And then if you compact it, the volume reduce, the compacted drive density is increasing in there. So there relationship between that. ZAV stand for zero air voice, if you recall that. So with that, let me give some equation how that change and how to capture that change in volume for different conditions. So the first one, if we transfer the soil from the bank to the loose, and it measured by swell percent, swell in percent, and it equal to 1 over load factor minus 1 and time 100 because that is percent. And what is load factor? Or also call it a swell factor. Load factor, also known as swell factor. It equal to loose density divided by bank density. And then if we change the volume from bank condition to compacted condition, then we have a shrinkage percentage. Shrinkage percentage. And in this case, it equal to 1 minus shrinkage factor times 100. And again, what is shrinkage factor? Shrinkage factor it equal to bank density divided by compacted density. And as you can see, for the loose density and bank density, the volume of loose is greater than the volume for the bank condition. So for that reason, as you can see, the loose density always less than the bank density. So load factors always less than 1. For shrinkage factor, the bank density and compacted density, as I show you in graphic in slide, you refer to slide, the bank density also tend to be less than the compacted density, except the rock that I will show you in a minute. Shrinkage factor tend to be less than 1, except the rock. And that I'm going to show you now for different type of material, what is swell percentage, load factor, shrinkage percentage, shrinkage factor look like. Let's go to the next slide. You can see here. For general, as you can see, for the bank, for example, at the natural condition, 1 cubic yard, when you disturb, excavate, put in the dump truck, it can increase 25% swell. And then we put on the side to compact it, for example, underneath of the pavement or underneath of the house, the volume it become 0.8 cubic yard, 20% shrinkage, as you can see here. So what does that mean? From the engineering standpoint, if you design a road or a building and you need, for example, 100 cubic yard to be filled in your site, your building or your project, then if you want to buy the material, it's not about 100 cubic yard that you buy. You need, for this condition, for example, you need to have 20% more, which is, it can be go up to 120 cubic yard for the bank. Okay, so that important concept that we have to understand how the volume change affect everything from the design perspective, from the estimating perspective, from the operation of the equipment, etc. So for different material, as you can see here, different material, we have different material we have here. So we have clay. We have that is in chapter 2, and we have the unit weight, which is the density for loose, bank, compacted, And as you can see, the pattern is what we predicted: the density of loose less than bank and less than compacted, and they have different swell percentage, shrinkage percentage, load factor, and shrinkage factor. And all it tend to be, you see the shrinkage factor and the load factor tend to be in the last two columns tend to be less than 1, except the rock, which is the third row in here. And you can see the shrinkage factor at 1.3, because for the rock, regardless of how after you blast it, you disturb the rock, how good you disturb the material, the volume of the compacted never be smaller than the natural of the rock. So for that reason, the shrinkage factor is greater than 1 for the rock. And if the problem don't give you any other information, they just give you the type of material, for example, clay, common earth, rock, or sand and gravel. So you use this table to solve the problem. So let me go back to give an example of the problem in here to solve. Okay, so that is the problem 1 that we have here. Soil weight 2,800 pounds per cubic yard in natural state. And so natural state, so that you can see that is a bank condition. 2,000 pounds per cubic yard excavation, after excavation, that is loose. And 3,500 pounds per cubic yard after compaction, so compacted. The question is find the swell factor, load factor, shrinkage factor for the soil. So as you can see, we just apply the equation for swell factor. So as you can see, the A, swell factor or load factor, from the equation we have above, right? Loose density, bank density. So loose 2,000 pounds per cubic yard. Natural state bank density 28. So from that you can get 0.71, and that is the first answer that you have. And then we also have swell percent. We also have the equation equal to 1 over swell factor or load factor, which is 0.71 minus 1 times 100. So from that we will have 40%. And what does that mean? For this type of soil, if we disturb, the volume increase 40%. And similarly, we have shrinkage factor. And that equal to bank density divided by compacted density. Bank density 28, compacted 35 pounds per cubic yard. It will be 0.8. And then we have shrinkage percent. It equal to 1 minus shrinkage factor 0.8 times 100. So it will be 20%. So what does that mean, shrinkage percentage? The volume at the natural condition, if changed to compacted, it reduced 20%. And that we can apply B easily. How many bank cubic yard and compacted cubic yard are contained in 1 million loose cubic yard? So as you can see here, we already have loose cubic yard. That is the question given. E loose equal to 1 million. And loose cubic yard, so it, as you can see, cubic yard is not enough. We say at LCY, loose cubic yard. Okay, so LCY stands for loose cubic yard. And what is the bank? So to find out the bank cubic yard, so we have VB equal to the equation equal to V loose times the load factor. And at a rule of thumb that you can see, it always the volume of bank less than loose volume. So we have 1 million times Load factor for this problem is square factor, 0.71. So it will be 710,000 cubic yard. But that's not enough. We say that BCY. Okay, so that B stands for bank cubic yard. L stands for loose. And the last one, what is the volume of the compacted cubic yard? So again, compacted transfer from the bank, not from the loose. So you have to start with the V bank, not V loose. From the original condition to the final condition compacted, and time the shrinkage factor. Shrinkage factor. And that equal to, as you can see, 0.71 million time shrinkage factor 0.8. And that we have equal to 568,000 CY, but not enough. It have to be CCY, and C stand for compacted. So what does that mean? That you can see you have 1 million loose cubic yard after you compacted is reduced almost half. So that the importance of see the volume change for different conditions of the earth. So with that, we close for the first portion of this lesson, and we move to the next video. We will talk about how to determine the volume for different geometrical shape.